Welcome back to geometry. We want to continue taking a look at section 16. And what I'm going to do is I'm actually going to skip to the end of the section to take a look at a theorem that we have here. And this theorem we already took a look at back in section 3. And it's the 30-60-90 triangle theorem. So we don't have the Pythagorean theorem right now, so we can't use that. But we want to be able to show this theorem without using the Pythagorean theorem and of course only using the theorems that we have available to us, theorems and postulates, axioms, those things. So if we have a 30-60-90 degree triangle, let triangle ABC be such, actually no, we don't want it to be such triangle. We want to go if and only if here. So let's just say we have a triangle. If the this short side is half the length, right? Let's see here. A, B, no. A, B, C. AB is 1/2 of BC if and only if we have that B is 60 degrees, and C is 30 degrees. We are given here as an assumption that A is 90 degrees. So right angle there. So this theorem we would like to prove, but in order to do that, we need to develop just one more tool. Before we can develop that tool, we need a definition. So this is where we want to go with what we're about to take a look at. And of course, it will be left for you to take a look at. So a median. A median of a triangle is a line segment whose endpoints are a vertex of the triangle and the midpoint of the opposite side. So vertex to midpoint of the opposite side. And we could go vertex to midpoint of opposite side or vertex to midpoint of opposite side. It doesn't really matter. They're all medians. However, for this theorem, we specifically want to talk about in a right triangle, the length of the median from the length of the median to the hypotenuse. So if it's to the hypotenuse, then it came from the right angle. The length of the median to the hypotenuse is half of the length of the hypotenuse. So AM is equal to 1/2 of BC. According to this diagram. All right, so we want to look at the proof of this theorem. And this is a little bit longer proof. So this will be the majority of our video. All right, let's start off with the things that we're given. M is the midpoint of line BC. Okay. We also know that we're working with a right triangle, so let's say that the measure of angle BAC is equal to 90 degrees. And these are given. All right. So we want to, if we wanted to show this, what we would recognize, or what we would want to recognize, is that this angle measure and this angle measure are the same. But we don't know how to prove that, right? What we have is an isosceles triangle here. If we were talking about having this embedded in a coordinate system, then we could probably prove this pretty easily just by looking at what the coordinates should be. But we don't have that. So if we want to get this, what we want to do is we want to construct a congruent triangle so that let's call this D, that ADC is congruent to ADC is congruent to CBA. So we want to construct this, but we have to do that in parts, of course. So the first thing to do is to recognize that this was a right angle and that we can find a line that is parallel to AB through C. So let's throw that in there. So we can find a line that is parallel to AB through C. Okay, and that's by the Euclidean parallel postulate. So let's go with that first. There exists a unique line, we'll call it L, that goes through C and parallel to AB. So this is line L. And we get this from the Euclidean parallel postulate. Excellent. So if we were to consider the ray AM passing through AB must also pass through L by the transversal parallels theorem. So the ray from A to M must intersect L at D. So let's call this point D, where AM intersects L. And this is, again, by the transversal parallel theorem. So let's draw that line as well. So it's going from A through M. It's going to hit the point D. That looks pretty good. Okay. Next, we have a few observations that we can make. The first being that if we look at the measure of angle 1, the measure of angle 2, we can compare those to 3 and 4. So angle 1 and angle 4 are congruent because we have a alternate interior angles here. So angle 1 is congruent to angle 4. We also have that angle 2 is congruent to angle 3. Excellent. And this is by the converse of the alternate interior angles theorem. So we want to get that 3 is actually congruent to 1, and we want to get that, well, we know that this is a 90-degree angle, and this is a 90-degree angle. But we also want to get that if we got that this angle and that angle are congruent, then we would have angle doesn't give us a congruent triangle. So we got to figure out an angle side angle. That's what we need, or angle side angle or side angle side. Lots of options. Anyway, so we're going to end up doing an angle side. So our next step is to recognize that M is a midpoint. So we have that BM is equal to MC. BM is equal to MC, which is 1/2 of BC, simply by the definition of midpoint. So we have that triangles ABM and let's see here, CDM are congruent, which gets us somewhere. Not quite where we wanted to overall, but it gets us somewhere. Okay, so 5, 6, triangle ABM. ABM is congruent to DCM. It's congruent to triangle DCM. And this is angle, angle, side. Angle, angle, side. For A, for B, and 5. But that does get us some really nice things. So we have that AM, or actually here, I wanted to say AM is congruent to MD, but that's not where I'm going with this. So we have AB is congruent to CD. Excellent. Yep, that's a bigger triangle congruency, so we're looking for that. So we have AB is congruent to line segment AB is congruent to the line segment from C to D. And this is by the definition of alternate interior, not definition of alternate interior angles, the definition of congruent triangles. Okay, so with that, so we have side and side. We know that both of these are right angles, so we can recognize that AC is congruent to itself and get side angle side. So AC, line segment AC is congruent to line segment AC because of the reflexive property of congruence. All right. So we haven't observed necessarily yet that this angle measure is 90, but we have that this line and that line are perpendicular and that this line and this line are parallel. So if these two lines are parallel and this line is perpendicular to that one, then this one is perpendicular to that one, given by the converse of parallel perpendiculars corollary. All right, so step 9 is that we get that the line L is in fact perpendicular to the line segment AC by the parallel, the converse of the parallel perpendiculars corollary. Excellent. This proof is several steps long. We've got 5 more steps to go yet after this, so 6 really. Let's see here. Since they are, since L is perpendicular, we get the measure of angle ACD is in fact 90. Measure of angle ACD is equal to 90 degrees. By the definition of perpendicular lines, which allows us to recognize that the measure or that angle ACD is congruent to CAB. Let's see here. Yes. And that's given by 1B and 10 and the transitive property of equality. Oh, so maybe I don't want to use congruence here. There we go. Measure of angle, measure of angle. Now I can cite the transitive property of equality. Cool. So this gives us angle. We had congruent sides, and we have angles. Oh no, we have side, side, and angle that connects them. That's where we were, right? BA is congruent to DC, AC is congruent to AC, and then now we have that both of these are 90 degrees. So side, angle, side, side, angle, side. So triangle ABC is congruent to, oh, actually here, let's, we want to say this wisely. Triangle BAC is congruent to triangle DCA by side, angle, side, 7, 11, 8. Okay, so now that we're here, right, we did as we wanted to before, talk about how this measure is equal to that measure, and observe that that we have an isosceles triangle. Which is not necessarily where we go with this. It's a little bit shorter, actually. So let's call and oh no, I'm sorry, we do use that. It's an isosceles triangle. So this is, we'll call this angle 5 and call this angle 6. I overlooked what we were doing there. I knew the idea, overlooked some details. So angle 5 is congruent to angle 6 as we wanted, and that's by the definition of triangles, which tells us that AM is in fact equal to MC. AM is equal to MC by the isosceles triangle theorem. The triangle that we're looking at in this case, of course, is AMC. All right, but we have all the way up here, BM is equal to MC is 1/2 of BC. So we can take AM, plug it into here, and get that AM is 1/2 of BC, which is what we want. So we get that AM is 1/2 of BC by substituting line 14 into line 5. Right there. Oh, or line 5 into 14, right? Replace MC with 1/2 BC. That's fine. But either way we go, we get what we wanted. And with that, you'll be able to approach this theorem in the homework or in the exercises using the previous theorem, right? The one that we just showed, along with theorem 16.2, right? This is the problem that asks you to do this proof. So you can take a look at that. All right, but that's it, right? That's the end of the section. So if you have any questions, of course, get in touch with me, let me know. and I will see you guys again soon.